Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Klingberg, your host. Today I'm going to talk about and demonstrate some things having to do with keeping the wings attached to the center section. And given that that's kind of a critical item, let's get on with it. Here we go. Okay, welcome back. As you may remember from the little tour video I put up of bonding the attachment fittings onto the main spar, we have some half-inch thick carbon fiber plates here, attachment fittings, which are bonded directly on to the shear web, and embedded in the shear web are the spar caps. If you watch the video on actually building these spars, you'll see how the spar caps are actually on the side of the shear web, which is a little different. Usually with the I-beam spar, the spar caps are on top, but you can put them down here too. And that's what I chose to do for this type of arrangement. And these fittings here are essentially a fork, a single fork fitting, and they slide over the shear web and are bonded on. Now, some astute observers of the videos out there said, whoa, that doesn't look like enough bonding area to take all the loads. And those people are probably either trained engineers or they're very good natural engineers, because they've spotted a fact, actually. The total bonding area here, this side and the other side, is 7.5 square inches. The adhesive that I'm using, the structural adhesive, is T88. It's good to about 2,000 psi. I use an average value. It runs between 1,800 and about 2,500 psi. So I use 2,000 as a way of calculating what loads a fitting can carry, or any attachment. So there's 7.5 square inches of area here, counting both sides, and the 7.5 square inches will carry 15,000 pounds of load. Well, what do you know? There's about 30,000 pounds of load that has to go through this fitting at 9 Gs. 30,000 pounds, that's a lot. So we have to somehow increase the bonding area to take all of those loads. So I could make this fitting longer this way, and I'd have more bond area. I could make the fitting thicker this way. I'd have more bond area. I could do an overwrap, and kind of spread out the loads that way. All of those have their own attending problems with them. Most of them are just bulky and heavy. Trying to make this fitting longer, this shape fitting out a half-inch thick plate, and making this taper very, very shallow as it goes out here, it'd be very hard to build accurately. There's a manageable length for working with this stuff, so that's why this fitting's the length that it is. Plus, this length of fitting happens to come out of standard size plate. So to buy the next size plate stock up, very expensive, and you end up wasting material. So it just really wasn't an answer. Doing an overwrap on the top of this, well, it's kind of hard to say how much actual strength that adds in terms of bonding it on. So what I've decided to do, and if you watch the construction of the center section of the wing, I use these pull-truded carbon fiber strips, and I'm going to do the same thing with these fittings. Now, this happens to be actually 2 strips joined together here, and 2 of them together makes them a half-inch wide. I have them joined together with some clear plastic tape for the bonding process, and after I'm done bonding them, I remove that tape for final bonding of the parts. So this piece is 80 inches long, give or take a little, and it bonds on to the side here like this, and wraps around this fitting here, and of course it's springy, so it's going to stick out a little here, but it wraps around the fitting and then bonds down the other side. So that this load strap, as I like to call it, is the same size as the height of the fitting, and it gets bonded to the shear web here, to the carbon fiber that's on the shear web, which is bonded to the spar caps underneath. So this load strap is transferring loads into and out of the spar caps that are embedded in the wing. Now, by stretching this bond length, this is very lightweight. There's not much weight in this. Each one of these strips, each one of these individual strips can take 1,200 pounds of tensile load. So two of them together, 2,400 pounds. Two sides, 4,800 pounds. So we've added 4,800 pounds of load that we can carry in this fitting just due to these two strips that I'm adding. Now, the fitting here, it's about a 1/2 inch by 3/4 of an inch, and that's good to about 70,000 PSI for this rated material. Now, the material that I'm using here is actually spec'd and measured and tested. You pay a lot for that, but you're assured of what loads it can carry, and this is good up to about 140,000 PSI, 150,000 PSI. So I know that with this arrangement, the tensile tear out here is about 70,000 pounds. So that's double what I need in terms of the maximum loads that'll be on the aircraft. So that's okay. We're adding another 4,800 pounds of load that we can carry this way. Well, that's nice to have, a little bit of extra, doesn't weigh much. But the important part is I'm adding a whole bunch of length here, along here, bonding length. And believe it or not, from the end of the fitting to the end of this strip, even though it's only a 1/2 inch wide, adds about 25,000 pounds of load that you can carry. Two sides, 50,000 pounds. So we can carry 15,000 pounds in the bonding of the fitting here, and we can carry an additional 50 with this strap. So it's a huge increase. Small increase in weight, huge increase in the load that it can carry in terms of tensile load and keeping this fitting attached to the shear web, which of course is the critical item. Heaven forbid these pull out. Now, I'm kind of an old guy at this. I've been at this for more than 40 years, and even though I've been working with composites for 25, 30 years, it still gives me the willies to think that everything here is dependent upon the bond strength, that the fittings, everything else, it's all held together with glue. I am accustomed to having bolts and welding and rivets, mechanical fasteners that we can count on. Well, you can count on bonding too. And mechanical fasteners, when we design for that, we design in margin. Designing in margin here, it's just that the psychological barrier of going from metal and wood aircraft, and by the way, wood aircraft are generally mostly bonded, but they have mechanical fittings also, especially in this area. But to go strictly to adhesive bonding for all of your attachment strength is a bit of a leap of faith. So I got plenty of margin on this thing. Almost a factor of 3, factor of 2.5 margin. Now that does add some weight, but it makes me feel better. And you'll say, well, gee, why didn't you run some mechanical fasteners in here? Why don't you run a bolt through here and grab onto that spar cap? Well, the spar cap is pull-truded carbon fiber, and it's really not amenable to running fittings through it. All of these composite materials are not isotropic. Metal fittings are isotropic in terms of they have the same qualities in every direction. Not true of composite materials. And because these are all unidirectional, this cap, the spar caps, tear out strength is limited, extremely limited. They tear out quite easily. So we cannot treat these the same. You cannot just slap a fitting through there, sock some rivets on here, boom, 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 and say you're all good, because you actually, rather than increasing the strength, might actually be decreasing it. So we have to, in order to achieve these really high strength to weight ratios, we have to work with the materials that we're given. And this spar cap is only a 1/2 inch tall, and it's about 1 inch tall, a little less than 1 inch tall, and it's only 1 millimeter thick. It's really, really thin, but tremendously strong, but not amenable to mechanical fasteners. So we have to bond it. And we have to bond it in such a way that we have enough margin that we'll always be confident that these bond lines will not fail. And if you look at the aerospace industry right now, especially some of the transport jets, they're being built out of carbon fiber now. And if you look closely at them, they're actually bonded and riveted and or bolted together. And they're not getting maximum advantage out of the composite materials. They're just being extra safe because those are commercial aircraft. And people that work in designing composite materials often call that black aluminum. They're building, designing, and using the materials as if they were aluminum. And they're missing out on some of the capabilities that the materials have. For this aircraft, I have to push it right to the limit to keep the strength to weight ratio high enough, so we can't be doing black aluminum, no mechanical fasteners. So we have to depend on the bond. Now, what I don't think anybody has noticed yet is the really critical factor here. The bond area, we got that covered in spades. But what's interesting is that this is tapered. This goes on here and this goes up here. Well, when you put a tension load on this, it wants to straighten out that strap, and it wants to go straight from here to some point out here, not to this point. So there's actually a lifting force that occurs. There's a force that occurs in this direction. When you put tension on this strap, you put tension on it this way, when there's a kink in it, it wants to straighten out. So there's a load going this way when you put it under tension. And that's a lifting load from the bond line where it's bonded down here. And that means that that bond line is being put in tension initially. It starts out as tension. If it were to pop loose, then it's in a peeling motion, a combination of tension and peel, which is very bad. Epoxies do not do well in peel at all. Very, very low strength that way. So we want to avoid peeling whenever possible. And in tension, they do so-so. Now this epoxy is good for 7,000 psi in tension. So then we have to find out, well, what is the tension load that's on here, the perpendicular coming away from the shear web trying to straighten this out? I've made that calculation. This is about a 5-degree angle here. And if we take the maximum load to sine of 5 degrees, turns out it's about 2,850 pounds. So over a ton of force going this way, trying to lift up that strap. However, if we look at this area of concern here, it's about 1 square inch. And the epoxy is good to 7,000 psi. It'll take about 3,500 pounds of load, this area here, and the epoxy is good to 7,000 psi. So double, almost double of what the load is here. And you think, well, that should be plenty of margin, and it should be. However, anytime you go on an angle like this, you go in like this, you turn a corner, when you're bonding this up, unless you're vacuum bagging, you do run a chance of having voids underneath. Now, you might be able to see here, I have some white filler here. I do put in structural filler in here so that when I put the strips on, it oozes into that filler, and that helps ensure that there are no voids, but you can't be guaranteed about that. And if you were to have a small void in here, well, then you don't have the area that you need to provide enough tensile strength to resist those lifting loads. So what you're going to see in the video here is I go through this whole process. You'll see a second phase at the end where I come back with an overwrap of carbon fiber. I'm actually going to wrap carbon fiber on the fitting. I'm going to go inside here, around the fitting, down, and then onto the shear web. So there's going to be like a channel on here that holds this strap tightly to the fitting and helps carry, it's a belt and suspenders. We'll essentially double the amount of lifting load that it can resist here. So better safe than sorry. A little extra weight for that. I'll add a few ounces to the aircraft, a little extra weight to give us the extra suspenders to hold it all together. But heaven forbid any of these fittings come loose in flight. It'd be the a very quick usage of the ballistic parachute because if these start to fail, it'd be catastrophic. Now, so the bottom line is this whole attachment arrangement is really designed to withstand probably 18 Gs. It has to be good to 9 Gs. That's the 6 Gs plus and minus, and then a 1.5 safety factor. So it's good for 18 Gs. If it's a lousy construction, a bad home builder, well, he's probably still safe. Got plenty of margin on it. And if there's any place to put margin, this is it. We don't want this to fail. If you got anywhere near 18 Gs, you have a lot of problems that are much worse than these fittings coming apart. There's going to be a whole slew of other problems you're more worried about. You probably already have the parachute out at that point. Way overbuilt, really strong, adds a little bit of weight to the aircraft. I'd say overall, by overbuilding this by a factor of 2, I would say it probably adds a pound to the aircraft, maybe a little bit more than that. Out of 100 pounds, 1%, it's something to think about, but I'd rather spend that pound here than somewhere else. It's a pound well spent. So stick with the video as we go forward here. You'll see me actually bond this sucker on. I've done 3 of them already. And the reason that you're here for the last one is it took me 3 of these to figure out how to do it. The first one was disaster, near disaster. Second one went sort of okay. The third one went pretty smooth. And that's the process that you're going to see here. So watch the process closely. The steps that I do and the order that they're done in is critical to making this whole thing work out smoothly. And I hope you enjoy that video. And then at the very end, you'll see how I'm going to do the overwrap on here. And I haven't done any of those yet. I'll probably wait to the 4th one to film that so that I actually know how to do it before I show you how to do it. I hope you enjoy and learn something along the way, and here we go. Hi, welcome back. I squeezed myself back into the corner here so I can talk about the final aspect of bonding the wing attachment fittings onto the spar. So in the previous part you saw how I did the final securing of these fittings here with the load straps all the way around. You saw how those were installed. And I've talked about the lifting forces involved at the inflection point where those straps go down the taper of the fitting. Maybe it's better if I hold it up this way. It goes down the taper of that fitting and then goes out flat along the shear web. And we have to, I've done an overwrap to prevent the load straps from pulling loose by straightening out with the loads that are on them. In the next fast forward segment, you're going to see how I actually did this work. I'm using on this a 5.6 ounce twill cloth. It's a 2x2 twill, which is very drapable, very formable. And I eased the edges of the fittings slightly with sandpaper, just rounded them off a little bit. And you'll see me lay the cloth in here. I'll wet out the surface first, and I lay the cloth in. Of course, everything is cleaned carefully with alcohol first to take all the grease off. I'm using T88 structural adhesive to actually do the wetting out. Because I'm bonding to a surface that's already been cured, we need an epoxy that is appropriate for a cured surface or a secondary bond. T88 does very well at that. And rather than wet out the cloth with some other type of resin and put T88 on the surface so I get a good bond, I just use the T88 to wet it out. And it requires that I use a heat gun a little bit to soften up the T88. It's pretty thick. So that it'll penetrate through the cloth. So basically I come in with a piece of cloth that's been taped off on the edges so it doesn't fray. The 2x2 twill is very easy to fray. And I get it wetted out and basically put in place. And then I cut the tape loose because the tape prevents it from forming all the way. It keeps it a little stiffer than you want it to be. But once it's wetted out, you can cut the tape away, and then it doesn't fray nearly as easily once it's been wetted out. And you'll see me go through that process here. And then once I have the tape removed and the cloth is all wetted out, then it's a matter of getting it shaped around the fitting. Now the fitting has some pretty sharp corners on it, both inside corners and outside corners. And if you would just try to glue that cloth down slowly before the epoxy cures, it's going to flatten out and pull loose, and it's not going to hold tight. And what we want a channel that has this kind of shape in the cloth that fits over this fitting and secures those load straps to the fitting. Make sure that they don't lift. And in order to do that, it just requires some formers. And I just do that very inexpensively. I have some pieces of spruce here, spruce stick. I've covered them in plastic packing tape, and then I spray them with a mold release. And currently I've been using a Teflon-based lubricant as my mold release. Works really good. As long as you don't have to bond to it a final time. There's no more bonding that's going to occur here, so using Teflon spray on these molding jigs is appropriate. And you'll see how I come in with this. I'll have the cloth in place, and then I come in first with the fitting that holds the cloth tight to the fitting itself, like this, right on top of the fitting. And then I come in with the sticks on the sides and actually push down on that cloth so that it's fitting tight to the sides of the fitting and tight to the shear web, and get right in the corner like that. And then there's one on the other side that fits between the flange and the fitting itself. The space between the fitting and the flange is 1/4 inch, so I got a 1/4 inch piece of wood here, and I squeeze those babies down in there. Got the one on top, and then have a clamp on this one. Get the side ones in there, put some other side clamps on it. It's a little bit tricky work, but you know, after a little practice, I got it pretty smoothed out, and you'll see that in the fast forward video. It really goes pretty easy. So we have one layer of carbon fiber cloth that goes over the top of this fitting and keeps the load straps attached to the fitting. Make sure that they don't lift up. It's a good belt and suspenders, and it doesn't add much weight. So let's go to the video and see how I actually did it. I appreciate you sticking around to the end of all these long videos while I ramble on, and ask you kindly to please consider subscribing, and maybe you'd like to visit my Patreon site that has all of the technical information or additional technical information, and pop a couple of bucks into the pot there and help keep this project going. So all of that rambling gone by, let's get on with actually doing this final overwrap and give us the final 18 G's of load carrying capability in these fittings. Here we go.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors, forever free. step back to see the truth around you. From a distance you can tell. You and me were meant to be.